Hi all. The last section of our chapter 3 is going to be talking about nonlinear inequalities. When we talk about nonlinear inequalities, that's going to consist of polynomial and rational inequalities. The reason we're going to be talking about these so much is that this topic is going to come up again in our calculus classes whenever we talk about the first and second derivative sign tests. So you'll notice in these problems I'll mainly be referring to sign changes and whenever the function is positive or negative, how that's going to impact our answer. Now, so if I look at this one with you, for an example, if I ask you to solve the inequality x squared is strictly less than 7x. Okay, so I have the steps here of the solution process to this. The very first thing, just like if it was an equation that you was trying to solve, you get a 0 on one side. Well, in an inequality, that's the same thing I want to do. I want to get a 0 on one side. So I say get the polynomial or rational expression compared to 0. In this case, it's a polynomial. I'll say x squared minus 7x is strictly less than 0. Now, the side that you have the x terms on, you need to factor that. So second step, I say completely factor. Notice I can factor by greatest common factor. I can factor out a common factor of x, and I'll have x times x minus 7. Now I say determine the zeros for each factor. This is where you're really not even going to treat it as an inequality anymore. You treat it as an equation, at least temporarily, to find the zeros. Those zeros are going to be points, in fact, often books call them boundary points. They're going to be points that are the boundary between solution and non-solution regions. So to find out when x times x minus 7 is less than 0, I first find out when it's equal to 0. So that's going to be when x is 0 and when x minus 7 is 0, or at x equals 7. Now, from those boundary points that our zeros exist at, we're going to create test intervals. So the test intervals automatically break up the domain of my function. Well, this was a polynomial function. It had an infinite domain from negative to positive infinity. So please notice my test intervals that I broke it down into. I said, well, 0 was my lowest, at 0 in this case, the x value solution at 0 is my lowest boundary point. So I'm going to go from negative infinity up to 0. Then I'm going to test any value in between 0 and 7. And then I'm going to test any value from 7 on to infinity. Now, I'm going to create test points within each of these test intervals to represent that interval. Now, the values I've chosen here, nothing special other than they are in the interval they're trying to represent. So you'll notice when I do test points here, a number between negative infinity and 0, I chose negative 2. Some number between 0 and 7, I chose a positive 2. And then some number between 7 and infinity, I chose 10. Now, the goal of this problem was to get x times x minus 7 to be less than 0. So that's what I'm trying to test in this case. X times x minus 7 needs to be less than 0. Now notice what I've done, and keep in mind I only care about the sign. So if I tell you to plug a negative 2 into this expression, you say, well, a negative 2 is going to make that first term negative. It would make the second term negative 2 minus 7 would be negative 9. Notice I don't need a negative 2 times a negative 9. All I need to know is that it's a negative number times a negative number. The product of any two negatives is a positive. I automatically know that this solution or that this region cannot be a solution, and the reason it's not a solution is because it's positive. There's no positive number in existence that's less than 0. Now, if you wanted to plug in the negative 2 and get, well, negative 2 times a negative 9 is a positive 18, you could, and you could see 18 is not less than 0. You could still see it's not a solution. But the point I'm trying to make here is that it's a sign test. Any positive number cannot be less than 0, so this region cannot be a solution. I go into my my next region, which is represented by 2. If I plug a 2 in this equation, I would get 2 times negative 5. Well, that's a positive times a negative. Any positive times a negative is a negative, and I want my region to be negative. I needed I needed it to be less than 0. So as soon as I see that this region is a negative, I say, the second region is a solution. My solution will contain the values of x between 0 and 7. Now I'm testing the values between 7 and infinity with a 10. If you plug a 10 in, you would have 10 times 3. Of course, that's a positive 30. Notice down here, I just said, well, it's going to be a positive factor times a positive factor, which is a positive product. There's no positive number in existence that's less than 0, so automatically we know this region is not a solution. So my only solution region is this middle region. You can say, well, then therefore, your answer in terms of interval notation, x is equal to all values of x between 0 and 7, not including the endpoints, because it had to be strictly less than 0. And at those endpoints, I know its values where the function is equal to 0. So those cannot be included in this case, so I have to put parentheses around them. The next polynomial inequality I want to look at with you. So I have the polynomial x cubed plus x squared is greater than or equal to 20x. First step on your other page, get 0 on one side. Notice that's what I've done. I've subtracted 20x on both sides. Then after that, you can say, well, okay, once you factor out the x out of the 3 terms here, clearly that comes out, you'd have a trinomial left over. In this trinomial, I was just thinking, okay, factors of negative 20 that sum to get to positive 1. I know 5 times negative 4 is a negative 20. 5 plus negative 4 is positive 1. So I know that this trinomial factors to x times x plus 5 times x minus 4. Now, finding your zeros, you just say, well, set each factor equal to 0. So I would get x equals 0, x plus 5 equals 0, which gives you x equals negative 5. And x minus 4 is equal to 0, which gives you x equals 4. Now, from those zeros, also known as boundary points, we set up our solution region. So you say, well, the first potential test region for my solution is going to be all values from negative infinity up to the leftmost boundary point of negative 5. So I say from negative infinity to negative 5. Then I would say from negative 5 to 0. Then from 0 to the next 0 at 4. From 0 to 4, and then you'd say from 4 to infinity. Please notice you had 3 zeros in this problem when the function was equal to 0. So anytime you have 3 zeros, you're going to have more than 3, in other words 4 test intervals, because the first one has to go from negative infinity to the first one. Your last test interval is going to go from your last 0 all the way up to infinity. So you always have one more test interval than you do 0. That's always going to be the case. Now, in this first interval between negative infinity and negative 5, I chose negative 10. Nothing special about that other than it's in that region. My next one between negative 5 and 0, I chose a negative 2. Between 0 and 4, I chose a positive 2. And between 4 and infinity, I chose a 5. Now remember, the goal of this question is that we want this product to be greater than or equal to 0. So I say, okay, I need that product, x times x plus 5 times x minus 4, to be greater than or equal to 0. If I plug a negative 10 into that product, the first term would be negative 10. Second term would be negative 5. The only thing I care with is that it's negative. The third term would be a negative 14. We know a negative times a negative times a negative is a negative. Is that our solution? No! We need it to be greater than 0. There's no negative number in existence that's greater than 0. So automatically I know that first region, not a solution. I move on to negative 2. So my first factor is a negative 2. My second factor would be positive 3. My third factor would be negative 6. I have two negatives times a positive. Well, a negative times a negative is a positive. This whole product is a positive, thus it is a solution this time. Any positive number is going to be greater than 0. I go to my next region, I plug in a 2. My first factor would be positive 2. My second factor would be positive 7. Third factor, negative 2. 2 positive times a negative is a negative, thus I know that region cannot be a solution. The fourth and final region, I'm choosing a 5 to represent it. My first factor would be a 5, my second factor would be a 10, my third factor would be a positive 1. You have the product of three positive numbers, which is positive. So you can say, okay, in this case, we know that any region that gave me a value greater than 0 is a solution. That's going to occur in the second and fourth region. But now keep in mind, in this problem, unlike the first example I did with you, any answer that can give you a 0 must also be included in your solution. So I can say, okay, then all of these x values that yield a 0 have to be part of the solution. In other words, I have to have brackets around them. Please remember, anytime you have equal signs in your problem, you're going to have brackets in your answer. So I'll say, okay, my first region, the test region was -5 up to 0. Both -5 and 0 are values that yield a 0, so they both must be included. Ooh, and I did wrong notation there. Maybe that was just to get you to see and to emphasize the point here. So bad, John. I'll have to go in and say x is equal to bracket -5 up to 0 bracket. And again, it's because in this case, equaling 0 is part of my solution. Then I would say union. My next region that was a solution were the values between 4 and infinity. But I'd say, well, okay, yes, that was the test region. But I already know 4 is a value that yields a 0. And that is part of my solution. So I have to put a bracket around the 4. You will never, ever have a bracket around positive or negative infinity. So I'd say 4 to infinity, parenthesis there. And this would be our final answer as opposed to what I previously had circled. So I'll put a complete X over that. Okay, next problem. You're thinking polynomial inequalities. Okay, that seems pretty good. What if I start throwing rational functions at you? We know that we've already been graphing rational functions in earlier sections, and the graph is really not that bad at all. As in terms of trying to do this with it with an inequality, you need to remember that just like polynomials, a rational function is going to have a 0 when the numerator is equal to 0. But it's also going to have a vertical asymptote whenever the denominator is equal to 0. And remember, at a vertical asymptote, your function can go from negative infinity to positive infinity on either side of that. So that's certainly another value that you need to check. So as soon as I see any rational inequality like this, the first thing I'll do, so since it's already set equal to 0, and that needs to be your first step, just like before, first step, always get the polynomial rational expression compared to 0. Already done here. The second side, or the second step, already done because both the numerator and denominator are already factored. So then I just set those factors equal to 0. I can say, well, this polynomial is equal to 0 if the numerator is equal to 0. So I say x plus 4 equals 0. I'll get x equals -4. Now, on the other hand, this fraction does not exist if 3x minus 5 is equal to 0. So I specifically say here, I know 3x minus 5 cannot equal 0. And that's going to give me 3x cannot equal 5. And thus, x cannot equal 5/3 here. Okay, so I have the restricted value for x, and I know the value of x that leads to a 0. Both of these are going to become values that I need to split the domain up with. So I'll say, okay, the left one is the -4 here. My test intervals are going to go from negative infinity to -4. Then any value from -4 to 5/3. Then any value from 5/3 to positive infinity. Now, choosing the test points within each of these regions, you can say, okay, some value between negative infinity and -4. I chose a -5. Some value between -4 and 5/3. Anytime 0 is in a region, I always choose it. So 0 is in that region, I chose it as a test point. Then between 5/3 and infinity, I just chose 5. Now, I'm needing to plug these test points into my fraction up here, my rational equation. X plus 4 over 3x minus 5, and you'll notice I kind of write it as the diagonal sign down here so I won't take up so much room vertically in my table. You can do vertical fractions if you prefer. I was just doing them diagonal fractions to not take up so much vertical space. So in this first one, x plus 4 divided by 3x minus 5, I'm trying to plug in a negative 5. Well, clearly your numerator would be negative 5 plus 4, it's a negative 1. Your denominator would be 3 times negative 5 minus 5, it'd be a negative 20. But then you know a negative divided by a negative is always a positive, so then you can say, but is that what we need? No! We needed our rational function to be less than or equal to 0. There's no positive number in existence that's less than or equal to 0. So I know this first region is not a solution. I move to my second region where I'm plugging in a 0. Your numerator would be a positive 4, your denominator a negative 5. Positive over a negative is a negative. So you can say, hey, yeah, that region is a solution because any negative number is going to be less than 0. Check. Third region. I'm plugging in a 5 to test that region. Your numerator would be 9. Your denominator would be a positive 10. So you'd say, well, a positive over a positive is a positive, but a positive number is not less than 0. That region is not a solution. So then my only region that's a solution is the second region, so between negative 4 and 5/3. But please remember, in this equation, anything that can equal 0 should be included in your answer. Well, what makes this equation equal to 0? A value of x equals negative 4. So you'll see down here I say x equals negative 4 can be included in the answer, but the 5/3, and this is a common mistake students will make, they'll put bracket negative 4 to 5/3 bracket, but remember, you can't have a bracket around 5/3. The function can't even exist at that point. So the function cannot be less than or equal to 0 there because it doesn't even exist there. So your final answer would just be x equals bracket negative 4 to 5/3 parenthesis. Another one of these rational functions that's more fun, whenever you can tell the rational inequalities that are more fun, it's when they're not set equal to 0 in the first step. So this one, you have the rational inequality 3x minus 1 over x plus 6, and I'm saying that's strictly greater than 1. First step is to get it compared to 0. So I had to subtract 1 on both sides. Now be very careful when you subtract that 1. You say, well, the only way you can subtract that 1, and the only way you can subtract in general is if you have a common denominator. So when I look at that 1, I need to see it as, oh, that's minus the group x plus 6 over x plus 6. If you didn't get a common denominator, you could not combine those fractions. So I got a common denominator. Now in my numerator, I'll have 3x minus x is 2x. Negative 1 minus 6 gave me the minus 7. So I have a numerator of 2x minus 7, a denominator of x plus 6, and it's still strictly greater than 0. Now, the values at which my rational function would equal 0 is going to be, well, when the numerator is equal to 0. That numerator is equal to 0 when 2x is equal to 7. And I can say, okay, that means I can divide by 2, and x is equal to 7 over 2. I know that the rational function does not exist if the denominator is 0, so I say x plus 6 cannot equal 0. I'll get x cannot equal negative 6. So I know the value x cannot be, and I know the value of x that yields a 0. Both of these need to separate up the domain to form our test intervals in terms of x. So I'll say, okay, from negative infinity to negative 6 is my first region. Then it would go from negative 6 up to 7 over 2 for my second region. Then from 7 over 2 to infinity for my third region. You choose test points within each region. Some number between negative infinity and negative 6, I chose negative 10. Anytime 0 is in a region, I always choose it. 0 is between negative 6 and 7 over 2. And then a number between 7 over 2 and infinity, I chose a 10. Please remember, these test points that are representing these intervals must be plugged into your original or factored, I'll say, inequality here. The 2x minus 7 over x plus 3 needs to be strictly greater than 0. So that's what I know must be true. So in other words, these signs of my test points inside this function needs to be positive. Okay, when I plug in a negative 10, my numerator would be a negative 27. My denominator would be a negative 4. I know a negative over a negative is a positive. I know this region is a solution. I could put a check mark over there beside the first one. Typically, when the first one is a solution, then the second one's not. Don't take that for granted, though. You probably need to check it out. When I try to plug a 0 into the numerator, I get a -7. But when I try to plug a 0 into the denominator, I get a +6. I know a negative over a positive is a negative. There's no negative number in existence that's greater than 0, so that region is not a solution. Now I'm highly suspecting the third region to be a solution. Usually it's the yes, no, yes, and it's going to be in this case. 10 is representing the last region. When I try to plug a 10 into my answer, I would get 20 minus 7. You'd have a +13 in your numerator. Your denominator would be +16. A positive divided by a positive is a positive. I don't care the specific number. I know that any positive number is greater than 0. Thus, this region is going to yield a solution. So then I would say, okay, my solution is the first, my first group and the second group here, but I need to remember in this problem, it's not okay to equal 0, so you'll never ever have any brackets, and you'll just say, well, the answer is just -infinity to -6 union 7/2 to infinity, parentheses around everything. Hope this makes sense out of these polynomial and rational inequalities. Let me know if you have any questions.